Imagine standing at the edge of everything you've ever known, peering into an abyss so deep and ancient that the light reaching your eyes began its journey before your planet even existed. Now imagine that abyss staring back, revealing secrets that fundamentally challenge every assumption you've held about your place in the cosmos. On December 25, 2022, humanity opened its newest eye to the universe, and what it saw defied our wildest expectations, shattered our carefully constructed theories, and whispered of possibilities so profound that we're still struggling to comprehend their implications. The James Webb Space Telescope, a machine born from 3 decades of human ingenuity, $10 billion of investment, and the collective dreams of thousands of scientists, has spent its operational life doing something extraordinary. It hasn't just observed the universe. It has rewritten the very foundations of what we thought we knew about existence itself. What if everything you learned about the early universe was wrong? What if galaxies formed faster, stranger, and more magnificently than our best models predicted? What if the building blocks of life are scattered throughout the cosmos in ways we never imagined? These aren't hypothetical questions anymore. They're the reality that Webb has forced us to confront, one stunning revelation at a time. Before we journey through the 10 discoveries that have fundamentally altered our understanding of reality, let me ask you something. When you look up at the night sky, what do you actually see? If you're in a city, perhaps a handful of stars struggling against light pollution. If you're fortunate enough to stand beneath truly dark skies, maybe a few thousand pinpricks of light and the ghostly band of the Milky Way stretching overhead. But here's what should make your skin tingle with a mixture of wonder and existential uncertainty. Every photon of light that enters your eye is a messenger from the past, a time traveler that has journeyed across incomprehensible distances to reach you at this precise moment. The light from the nearest star beyond our sun left its surface over 4 years ago. The light from the Andromeda Galaxy, visible as a faint smudge to the naked eye, began its journey 2.5 million years ago, when your ancestors were barely recognizable as human. Now, the James Webb Space Telescope has pushed that boundary to unfathomable extremes, capturing light that has traveled for over 13 billion years, light that began its journey when the universe itself was a mere infant, still learning how to form the structures that would one day give rise to you, sitting here, contemplating its origins. The first discovery that shook the astronomical community to its core came within months of Webb's first science operations. Researchers using the telescope identified galaxies that shouldn't exist, at least not according to our established understanding of cosmic evolution. These weren't just distant galaxies. They were massive, fully formed spiral galaxies existing merely 200 to 300 million years after the Big Bang. To put this in perspective, imagine expecting to find a newborn infant and instead discovering a full-grown adult with decades of life experience already behind them. Our models of galaxy formation, painstakingly constructed over generations of observations and theoretical work, suggested that the early universe should be populated by small, irregular proto-galaxies, chaotic collections of stars slowly merging and growing into the majestic spiral and elliptical galaxies we see in our cosmic neighborhood today. The process should take billions of years, a gradual accumulation of matter guided by the invisible hand of dark matter and the relentless pull of gravity. But Webb revealed something different, something that sent cosmologists scrambling back to their computer simulations and theoretical frameworks. The telescope's infrared eyes, capable of seeing through the dust and across the vast expanses of spacetime, discovered galaxies designated Glass Z13, Glass Z11, and others in the Jade Survey that appeared remarkably mature for their cosmic age. These galaxies displayed well-defined structures, active star formation, and masses that seemed impossibly large given the limited time available for growth. Some of these ancient galaxies contained stellar populations approaching or exceeding 1 billion solar masses. Think about that for a moment. In the cosmic blink of an eye following the Big Bang, enough matter had coalesced, enough stars had formed, enough fusion had occurred to create galactic structures rivaling smaller galaxies we see in the modern universe. Ask yourself this question, and really sit with the implications. If galaxies formed this quickly, this efficiently, in the early universe, what does that tell us about the fundamental processes governing cosmic evolution? Were conditions in the early universe so dramatically different from what we imagined that our entire timeline of structure formation needs revision? Or is there something else at play, some mechanism or force we haven't yet identified that accelerated galaxy growth in those first few 100 million years? The scientists working with Webb data have proposed various theories, and it's crucial to understand these are speculations, educated hypotheses based on the available evidence but not yet confirmed. Some suggest that dark matter, that mysterious substance comprising 85% of all matter in the universe, might have been distributed differently in the early cosmos, creating deeper gravitational wells that pulled ordinary matter together more rapidly than current models predict. Others propose that the first generation of stars, massive behemoths burning with incredible fury, might have lived and died so quickly that they seeded their environments with heavy elements much faster than anticipated, accelerating subsequent generations of star formation. There's another possibility, one that's simultaneously exciting and humbling. Perhaps our entire understanding of how gravity operates on cosmic scales needs refinement. What if the equations we use to describe the large-scale structure of the universe, equations that have served us well in describing the local cosmos, break down under the extreme conditions of the early universe? This wouldn't be the first time in scientific history that a new observation forced us to revise fundamental physical laws. Newton's gravity worked perfectly well until we needed to describe extreme conditions, at which point Einstein's general relativity revealed a deeper, more accurate description of reality. Could we be standing at the threshold of another such revolution? The possibility sends shivers down the spines of physicists and astronomers alike. The second discovery takes us in a different direction entirely, from the largest structures in the universe to the question that haunts human consciousness perhaps more than any other. Are we alone? For decades, astronomers have been discovering planets orbiting distant stars, thousands upon thousands of worlds ranging from scorching hot Jupiters orbiting perilously close to their parent stars to frozen super-Earths lurking in the outer darkness of alien solar systems. But discovering that these planets exist is fundamentally different from understanding what they're actually like. It's the difference between knowing a house exists on a distant street and being able to peer through its windows to see who lives inside. The James Webb Space Telescope has given us that window, and what it revealed in the atmospheres of distant exoplanets represents nothing less than a new era in the search for life beyond Earth. WASP 39b, a planet located approximately 700 light-years from Earth, became one of Webb's first exoplanetary targets. This world is no Earth twin. It's a hot gas giant, a Saturn-sized planet orbiting so close to its star that it completes a full orbit in just over 4 days, with surface temperatures exceeding 800 degrees Celsius. It's not a place you'd want to visit, not a world where life as we know it could survive. But that's not what made astronomers lean forward in their chairs, hearts racing, as the data came in. Webb's spectrographic analysis, a technique that splits light into its component wavelengths to identify the chemical fingerprints of different molecules, revealed something extraordinary in WASP 39b's atmosphere. Carbon dioxide. Not just traces, but clear, unambiguous evidence of carbon dioxide molecules floating in the atmosphere of a planet orbiting a star hundreds of light-years away. Now, you might wonder why this matters. Carbon dioxide exists throughout the universe. We see it in the atmospheres of Venus and Mars. We exhale it with every breath. What makes its detection on a distant exoplanet so revolutionary? The answer lies not in the molecule itself, but in what its detection represents. This was the first definitive detection of carbon dioxide in an exoplanet atmosphere, but more importantly, it demonstrated that Webb possesses the sensitivity and precision to identify specific molecules in the thin atmospheric layers of distant worlds. If Webb can detect carbon dioxide, what else can it find? Could it identify the signatures of methane, ammonia, water vapor, or even the tantalizing biosignatures that might indicate the presence of life? The implications cascade outward like ripples on a cosmic pond. Webb has since analyzed the atmospheres of multiple exoplanets, including WASP 96b, where it detected clear evidence of water vapor and clouds, and LHS 475b, a rocky planet nearly identical in size to Earth. With each observation, Our catalog of alien atmospheres grows richer, more detailed, more nuanced. We're building a taxonomy of worlds, understanding how different planetary environments create different atmospheric compositions. We're learning which types of stars tend to have which types of planets with which types of atmospheres. We're taking the first halting steps toward answering that most profound of questions. In this vast universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, many of those stars surrounded by planets, are we truly alone, or does life in some form exist elsewhere? Here's a question for you to ponder, one that scientists and philosophers have debated for centuries. If Webb were to detect oxygen and methane simultaneously in the atmosphere of a rocky exoplanet in the habitable zone of its star, combinations of gases that on Earth are maintained by biological processes, would you accept that as evidence of extraterrestrial life? Or would you demand more proof, more data, more observations? What level of evidence would convince you that life has arisen independently on another world? And perhaps more unsettlingly, what would it mean for humanity's self-perception, our religions, our philosophies, our very sense of significance if we discovered we're not unique, not special, not alone? The third discovery returns us to the realm of the very old, the very distant, the very strange. Among the many puzzles that keep cosmologists awake at night, few are more perplexing than the question of supermassive black holes in the early universe. These gravitational monsters, objects millions or even billions of times more massive than our Sun, exist at the centers of most large galaxies, including our own Milky Way. The supermassive black hole at the heart of our galaxy, designated Sagittarius A star, contains the mass of approximately 4 million suns compressed into a region smaller than the orbit of Mercury. These objects are strange enough in the modern universe, but their existence in the ancient cosmos poses a profound problem that Webb has made significantly worse, or significantly more interesting, depending on your perspective. Black holes grow by consuming matter. Gas, dust, stars, anything that ventures too close to the event horizon gets drawn inexorably inward, adding its mass to the black hole's ever-increasing bulk. But this process takes time. Even under ideal conditions, with abundant fuel and efficient accretion, growing a black hole from stellar mass, the mass of a single collapsed star, to supermassive scale should require hundreds of millions or even billions of years. Here's the problem. We've known for years, thanks to previous observations, that supermassive black holes existed when the universe was less than 1 billion years old. This was already challenging to explain, requiring that black holes began growing essentially immediately after the Big Bang and maintained maximum possible growth rates for their entire existence. It was possible, just barely, to construct models that could produce these early supermassive black holes, but those models were stretched to their breaking points, requiring near-perfect conditions and a bit of theoretical luck. Then Webb looked deeper and found them even earlier. The telescope identified black holes existing merely 500 to 700 million years after the Big Bang, black holes already containing millions of solar masses. Some of these ancient behemoths are so massive and so early that they've forced astronomers to seriously question whether our understanding of black hole formation is fundamentally flawed. The most distant quasar observed by Webb, designated Surs 1019, hosts a black hole of approximately 9 million solar masses at a time when the universe was only 670 million years old. To put this in perspective using our earlier analogy, if the universe's current age is equivalent to a 50-year-old adult, we're finding supermassive black holes when the universe was barely 2 years old. How does a toddler universe create such monsters? Several theories have been proposed, and it's important to emphasize that these remain speculative, competing ideas that scientists are actively investigating and debating. The traditional model suggests that black holes form from the collapse of massive stars, creating what we call stellar mass black holes of perhaps 10 to 100 solar masses. These seeds then grow through accretion and mergers. But perhaps that's not the only path. Some theorists propose that in the dense, chaotic environment of the early universe, massive clouds of gas could have collapsed directly into black holes without ever forming stars first, creating what are called direct collapse black holes with initial masses of 10,000 to 100,000 solar masses. Starting with a more massive seed would give these black holes a significant head start in the race to supermassive status. Another possibility involves dark matter, that mysterious invisible substance we mentioned earlier. What if, under certain conditions, dark matter can collapse into black holes? Dark matter interacts gravitationally but doesn't interact with light, making it incredibly difficult to detect directly. If dark matter black holes could form and subsequently consume ordinary matter, they might grow to supermassive scales much more quickly than conventional models predict. This remains highly speculative, venturing into the territory of exotic physics that we haven't yet confirmed. But the observations Webb is providing are forcing scientists to consider previously fringe ideas with new seriousness. Consider this question carefully. What does it mean for our understanding of cosmic evolution if supermassive black holes existed before most galaxies had fully formed? Current models suggest a kind of chicken and egg relationship between galaxies and their central black holes, each influencing the other's growth. The black hole's intense radiation and powerful jets can regulate star formation in the surrounding galaxy, while the galaxy funnels gas inward to feed the black hole. But if black holes achieved supermassive status very early, before their host galaxies had matured, does that suggest that black holes might actually drive galaxy formation rather than being a consequence of it? Could these early black holes have served as the gravitational anchors around which the first major galaxies coalesced? The implications are staggering, suggesting a universe whose structure and evolution is even more intimately connected to these strange gravitational singularities than we ever imagined. The fourth discovery brings us to one of the most iconic images in astronomical history, reimagined with unprecedented clarity and revealing secrets hidden from previous generations of telescopes. In 1995, the Hubble Space Telescope captured an image that would become one of the most famous photographs ever taken. The pillars of creation, towering columns of gas and dust in the Eagle Nebula, approximately 7,000 light-years from Earth, became an instant icon, featured on posters, in documentaries, in science classrooms around the world. These weren't just pretty pictures. They were windows into the star formation process, showing massive clouds of molecular hydrogen being sculpted by the intense radiation from nearby young stars, even as new stars were being born within the pillars themselves. When Webb turned its infrared eyes toward the pillars of creation, astronomers knew they would see new details, but the results exceeded even optimistic expectations. Where Hubble saw obscuring dust, Webb's infrared vision penetrated the cosmic fog to reveal the pillars' secrets. The new images showed dozens of previously unknown young stars, still cocooned in their natal gas, lighting up the pillars from within like candles in ornate chandeliers. The three-dimensional structure of the pillars became clear in ways Hubble's visible light images couldn't capture, revealing how stellar winds and radiation are actively sculpting these cosmic monuments, carving them away layer by layer in a process that's both creative and destructive. But the true revelation wasn't just visual beauty, though Webb's images are undeniably breathtaking. The telescope's spectroscopic capabilities allowed scientists to analyze the chemical composition of the pillars with unprecedented precision. They found complex organic molecules, the carbon-based chemistry that forms the foundation of life as we know it. These weren't simple compounds. Webb detected polycyclic aromatic hydrocarbons, complex ringed molecules that on Earth are associated with combustion, but in space are created in the violent environments around dying stars and star-forming regions. These molecules are hardy, stable enough to survive in the harsh environment of space, and they're everywhere, scattered throughout star-forming regions across the galaxy. Here's where things get profound. The matter that makes up your body, every atom of carbon, nitrogen, oxygen, phosphorus, every element heavier than helium, was forged in the nuclear furnaces of stars that lived and died before our solar system formed. You are, quite literally, made of stardust, a fact that Carl Sagan famously emphasized and that remains no less awe-inspiring for its repetition. But Webb's observations of the pillars of creation and similar star-forming regions are showing us that it's not just atoms that are recycled through the cosmos. Complex organic molecules, the building blocks that might eventually assemble into the chemistry of life, are also being created in these stellar nurseries, scattered into space when massive stars die, incorporated into the next generation of solar systems, delivered to young planets where they might participate in the origin of life. This leads to a fascinating question. When life began on Earth approximately 3.5 to 4 billion years ago, emerging from the primordial chemistry of the young planet, was it starting from scratch, building complex organic molecules from simple components, or was it working with a head start, utilizing complex organic compounds delivered from space by comets and asteroids that had themselves inherited these molecules from the stellar nursery where our solar system formed? The discovery of complex organics in regions like the pillars of creation supports the hypothesis that the universe is seeding planets with the chemical building blocks of life, potentially making the origin of life, if not inevitable, at least significantly more probable than if every planet had to synthesize everything from basic elements. Some scientists have speculated, and again, this is speculation rather than established fact, that the prevalence of complex organic molecules in space might mean that the universe is essentially primed for life, that anywhere conditions are right, the chemistry needed to kickstart biological processes is already present, waiting for the right environment to transform from interesting chemistry into something we would recognize as living. Others are more cautious, pointing out that the gap between complex organic molecules and actual life is vast, requiring not just the right chemistry but the right organization, the right energy sources, the right environmental conditions maintained over millions or billions of years. The debate continues, but Webb's observations are providing crucial data points, showing us just how rich the cosmic chemistry really is. The fifth discovery takes us to the outer reaches of our own solar system, to the ice giant Neptune, a world so distant that it appears as little more than a tiny blue disk even in powerful Earth-based telescopes. Neptune orbits 30 times farther from the Sun than Earth does, receiving less than 1% of the sunlight we enjoy, making it a dim, cold, mysterious world that we've only visited once, during Voyager 2's brief flyby in 1989. That encounter revealed a dynamic atmosphere with the fastest winds in the solar system, strange dark spots that appear and disappear, and a system of thin, incomplete rings that were difficult to see from Earth. When Webb observed Neptune in its infrared wavelength range, something remarkable happened. The planet's rings, barely visible in most observations, appeared with stunning clarity, sharp and bright against the darkness of space. This wasn't just an aesthetic improvement. Webb revealed structures in Neptune's ring system that had never been seen before, showing the rings in more detail than at any time since the Voyager flyby over 30 years earlier. But Webb went further, capturing Neptune's moons, including Triton, the large captured moon that orbits Neptune backwards, suggesting it was born in the Kuiper Belt and later snared by Neptune's gravity. Triton is particularly interesting because it's geologically active despite being so far from the Sun that temperatures hover around -235 degrees Celsius. Voyager 2 observed geysers on Triton, plumes of nitrogen ice and gas erupting from beneath the surface, evidence of internal heat that shouldn't exist on such a cold, distant world. Webb's observations are helping scientists understand Triton's composition and thermal properties, building toward a more complete picture of this strange moon. Some planetary scientists have speculated that Triton, beneath its frozen surface, might harbor an internal ocean of liquid water, kept warm by tidal heating as Neptune's gravity squeezes and flexes the moon's interior. If true, Triton would join the ranks of potentially habitable worlds in our solar system, alongside Jupiter's moon Europa and Saturn's moon Enceladus, both of which are also thought to have subsurface oceans. But the significance of Webb's Neptune observations extends beyond this single planet. The ice giants, Neptune and Uranus, represent a class of planets that appears to be incredibly common in the galaxy. Many of the exoplanets we've discovered fall into the Neptune-sized category, worlds with masses between 10 and 20 times Earth's mass, likely composed of thick atmospheres surrounding rocky or icy cores. Yet Neptune and Uranus are the only ice giants we can study in detail, the only examples of this common planetary type that we can observe up close. Webb's ability to characterize Neptune's atmosphere, rings, and moons in infrared wavelengths provides a template for understanding similar worlds around other stars. The telescope detected methane in Neptune's atmosphere with unprecedented precision, mapping how it varies across the planet's disk and how it interacts with the atmospheric dynamics that drive those ferocious winds. This kind of detailed atmospheric characterization in our own solar system helps calibrate our techniques for analyzing exoplanet atmospheres. When Webb detects methane in the atmosphere of a distant Neptune-sized exoplanet, scientists can compare it to the methane distribution we see in our local Neptune, using our solar system as a laboratory to interpret what we're seeing light years away. Think about this for a moment. We're using one of the most powerful telescopes ever constructed, a machine designed to peer back to the dawn of time and search for signs of life around distant stars, to study a planet in our own cosmic backyard. Does that seem like a waste of precious observing time? Not at all. Understanding our own solar system, the only planetary system we can study in exquisite detail, provides the foundation for interpreting everything we see elsewhere. It's like learning to read by first mastering the alphabet. Neptune and the other solar system bodies that Webb observes are our alphabet, the reference points that allow us to decode the messages we're receiving from the wider universe. The sixth discovery might initially seem less dramatic than distant galaxies or exotic exoplanets, but it represents something profound about the nature of scientific progress and the architecture of the cosmos. Webb's deep field images, particularly the first deep field released in July 2022, showed a region of sky roughly equivalent to the size of a grain of sand held at arm's length. In that tiny patch of sky, Webb revealed thousands of galaxies, each one containing billions or hundreds of billions of stars, each of those stars potentially hosting planets, each of those planets a world as real and complex as Earth. The image showed galaxies stretching back through cosmic time, the most distant ones visible as tiny red smudges, their light stretched to infrared wavelengths by the expansion of the universe itself. But here's what makes this truly significant. Hubble took its deepest images by staring at the same patch of sky for days, accumulating photons, building up signal until faint galaxies emerged from the background noise. Webb achieved comparable or greater depth in a matter of hours. The telescope's larger mirror, 6.5 meters in diameter compared to Hubble's 2.4 meters, collects more light. Its infrared instruments are optimized for detecting the redshifted light of distant galaxies. The combination means Webb can see farther, faster, more efficiently than any previous observatory. This isn't just a technical achievement. It represents a fundamental expansion in our ability to study cosmic history. If Webb can reach extreme distances in hours rather than days, it means we can survey larger areas of the sky, study more galaxies, build better statistical samples of how galaxies evolve over cosmic time. Instead of examining one or two deep fields and hoping they're representative of the universe as a whole, Webb can observe dozens or hundreds of regions, mapping out how galaxy properties vary across the sky and through cosmic time. This kind of comprehensive survey work is essential for moving beyond case studies to genuine understanding of cosmic evolution. The deep field images also revealed something unexpected about the distribution of galaxies in the early universe. Scientists had anticipated that as you look farther back in time, toward the first billion years after the Big Bang, galaxies would become increasingly rare, smaller, and more irregular. After all, the early universe should be catching galaxies in the act of forming, before they've had time to grow large and organized. But while galaxies in the deep fields do show evolutionary trends, with more irregular morphologies and higher rates of star formation at greater distances, they're also more numerous and more structured than some models predicted. This ties back to our first discovery about unexpectedly mature early galaxies, reinforcing the sense that the early universe was a more dynamic, faster evolving place than we thought. The images also highlight the role of gravitational lensing, a phenomenon predicted by Einstein's general relativity where the gravity of massive objects bends light, acting like a cosmic magnifying glass. Several of the galaxies in Webb's deep fields are visible only because they've been magnified by foreground galaxy clusters, their light bent and amplified by the curvature of space-time around the cluster's immense mass. Without this natural magnification, these galaxies would be too faint for even Webb to detect. It's a beautiful example of how the universe itself provides tools for exploration. How the same force that holds you to Earth's surface and governs the orbits of planets also enables us to see deeper into cosmic history. Consider this question. When you look at a deep field image containing thousands of galaxies, each galaxy containing billions of stars, the total number of stars in the image numbering in the trillions. How does that make you feel? Does it inspire wonder at the scale and beauty of creation? Does it provoke existential anxiety at your own insignificance in such vastness? Does it make you curious about what's happening right now on planets circling stars in those distant galaxies? There's no right answer, but the question itself reveals something about how we process information that challenges our intuitive sense of scale and significance. The seventh discovery brings us to Jupiter, the king of planets in our solar system. A gas giant so massive it contains more than twice the mass of all other planets combined. Jupiter might seem familiar, a planet we've studied for centuries, visited by multiple spacecraft, observed by professional and amateur astronomers alike. What could Webb possibly reveal about Jupiter that we don't already know? The answer came when the telescope turned its infrared gaze toward the giant planet and captured images of unprecedented clarity showing Jupiter's auroras, the massive polar light shows created as charged particles from the solar wind spiral down the planet's magnetic field lines and crash into the upper atmosphere. Earth's auroras, the northern and southern lights, are beautiful displays of green and red curtains of light shimmering across polar skies. They're created by interactions between the solar wind and Earth's magnetic field, and they're powered ultimately by the sun. Jupiter's auroras operate on a similar principle but at an almost incomprehensible scale. Jupiter's magnetic field is 20,000 times stronger than Earth's, extending millions of kilometers into space. The auroras at Jupiter's poles are larger than Earth itself, emitting more energy than all of human civilization uses in a year, creating a spectacular light show that's unfortunately invisible to human eyes because it occurs primarily in ultraviolet and infrared wavelengths. Webb's infrared instruments captured these auroras with stunning detail, but more importantly, they revealed new structures in Jupiter's upper atmosphere, showing how energy from the auroras interacts with and influences the atmospheric chemistry and dynamics. The images showed intricate patterns in Jupiter's polar regions, hazes and circulation patterns that hadn't been clearly visible in previous observations. This matters because Jupiter's atmosphere is a laboratory for understanding atmospheric physics under extreme conditions. The giant planet experiences storms larger than Earth, winds that blow at hundreds of kilometers per hour, and complex chemistry driven by both internal heat and solar radiation. But Webb's Jupiter observations did more than just provide pretty pictures. The telescope also observed Jupiter's moons, particularly Europa and Ganymede, two of the four large Galilean satellites. Europa is one of the most exciting places in the solar system from an astrobiological perspective. Beneath its icy surface lies an ocean of liquid water containing more water than all of Earth's oceans combined. This subsurface ocean is kept liquid by tidal heating, the same mechanism that might warm Triton's interior, as Jupiter's powerful gravity constantly squeezes and flexes Europa's interior, generating heat through friction. Where there's liquid water, energy, and chemistry, there's potential for life. Webb's observations are helping to characterize Europa's surface composition, looking for areas where subsurface material might have been brought to the surface, providing clues about what's in that hidden ocean. The telescope detected water ice, as expected, but also looked for salts, minerals, and organic compounds that could tell us about the ocean's chemistry. Future missions, including NASA's Europa Clipper and ESA's JUICE mission, will explore these moons in greater detail, but Webb's observations are providing crucial context, helping mission planners identify the most interesting targets for closer study. Ganymede, the largest moon in the solar system, bigger even than the planet Mercury, also likely harbors a subsurface ocean, though buried deeper beneath multiple layers of ice and rock. Webb's observations are building a more complete picture of Ganymede's surface and atmosphere. Yes, Ganymede has a thin oxygen atmosphere, helping scientists understand this complex world's geology and evolution. The fact that we can use Webb to study moons in our own solar system while simultaneously probing the distant universe speaks to the telescope's versatility and the interconnected nature of planetary science and astronomy. Ask yourself this. If life exists in Europa's subsurface ocean, adapted to a world of eternal darkness, deriving energy not from sunlight but from chemical reactions at the ocean floor, would we even recognize it as life? Would it be based on the same DNA and RNA chemistry that powers all life on Earth? Or might it have invented different solutions to the problems of metabolism, reproduction, and evolution? And if life has independently arisen in two places in the same solar system, Earth and Europa, what would that suggest about the prevalence of life in the universe as a whole? The statistics would shift dramatically. Life would go from being potentially rare and precious to almost certainly common, scattered across countless worlds in countless solar systems throughout the galaxy. The eighth discovery takes us into the realm of stellar archaeology, the study of ancient stars and the chemical enrichment of the universe over time. When the universe emerged from the Big Bang 13.8 billion years ago, it consisted almost entirely of hydrogen and helium, the two simplest elements. Everything else, every atom of carbon, oxygen, iron, silicon, gold, uranium, every element that makes up planets and people and everything you can touch and see, was forged later in the nuclear furnaces of stars or in the violent explosions that marked their deaths. The first generation of stars, known as population 3 stars, were massive, metal-free giants that lived fast and died young, exploding as supernovae and seeding their environments with the first heavy elements. We've never definitively observed a population 3 star. They existed so early in cosmic history, and their lifetimes were so brief, millions rather than billions of years, that none should still exist in their original form. But their chemical legacy persists in the next generations of stars, stars that formed from gas clouds enriched by those first stellar deaths. By studying the chemical compositions of very old stars and very distant galaxies, astronomers can work backward, reconstructing the history of cosmic chemical enrichment, understanding how the universe built up its periodic table element by element, generation by generation. Webb has observed some of the most distant and therefore most chemically primitive galaxies ever seen. Galaxies forming from gas that have been enriched by only 1 or 2 generations of stellar evolution. The spectra of these galaxies show different elemental abundances than modern galaxies like the Milky Way. They have more oxygen and carbon relative to iron, for instance, a pattern that reflects the different timescales on which different elements are produced. Oxygen and carbon are made in massive stars that die quickly, while iron is produced primarily in type Ia supernovae, which involve white dwarf stars and occur over longer timescales. By mapping out these abundance patterns at different cosmic epochs, Webb is helping to construct a chronology of stellar evolution and chemical enrichment. The telescope has also detected very metal-poor stars in our own galaxy, ancient relics from the Milky Way's early days. These stars are rare, but they're incredibly valuable because their chemical compositions preserve a record of the interstellar medium from which they formed billions of years ago. One particularly interesting finding involves the detection of unexpected abundance patterns that might indicate contribution from very rare stellar events, like parent stability supernovae or colliding neutron stars, events that produce unique elemental signatures and help explain the origin of the heaviest elements. There's a profound poetry in this work. Every element in your body has a story. The calcium in your bones was forged in massive stars that exploded as supernovae billions of years before the sun formed. The iron in your blood was synthesized in the cores of dying stars or in the explosive mergers of stellar remnants. The gold in any jewelry you might wear was created in the collision of neutron stars, incredibly dense stellar corpses smashing together with such violence that they briefly recreate the conditions of the Big Bang itself, fusing lighter elements into the heaviest stable and unstable elements in the periodic table. Webb's observations are helping us understand these processes in unprecedented detail, showing how the universe builds complexity from simplicity, how it transforms the primordial hydrogen and helium of the Big Bang into the rich chemical diversity that makes planets and life possible. Here's a question that bridges science and philosophy. Does it change how you think about your own existence to know that you are assembled from atoms that have cycled through multiple stars, that the matter making up your body is billions of years older than you are, that you are a temporary configuration of cosmic material that has existed in countless other forms and will exist in countless more after you're gone? Some find this perspective depressing, a reminder of impermanence and insignificance. Others find it profoundly connecting, a recognition that we are literally part of the universe, that the distinction between us and the cosmos is artificial, that we are the means by which the universe examines and understands itself. The ninth discovery ventures into one of the strangest and most fascinating predictions of modern physics. The theory of general relativity, Einstein's revolutionary description of gravity, predicts that space and time are not fixed, absolute backdrops against which events unfold, but rather dynamic entities that can be bent, warped, and stretched by the presence of mass and energy. One consequence of this is gravitational lensing, which we mentioned earlier. When light from a distant object passes close to a massive foreground object, the foreground object's gravity bends the path of the light, potentially creating multiple images of the background object or magnifying it or distorting it into arcs and rings. Webb has observed numerous examples of gravitational lensing, but some of the most spectacular involve what are called Einstein rings, situations where the alignment between the background object, the lensing mass, and the telescope is so perfect that the background object appears as a complete or partial ring around the foreground lens. These aren't just pretty pictures, though they are visually stunning. They're powerful scientific tools. By analyzing the properties of the lensing, astronomers can measure the mass of the foreground object with incredible precision, including the contribution from dark matter, which is otherwise invisible. They can also use the magnification effect to study the background object in far greater detail than would otherwise be possible. One particularly remarkable Webb observation involved a distant galaxy lensed by a foreground cluster in such a way that the background galaxy appeared multiple times in the same image, each image showing the galaxy at a slightly different moment in its past because the light traveled different path lengths to reach us. This might sound like science fiction, but it's a direct consequence of general relativity. Light following different paths through curved spacetime takes different amounts of time to reach the observer. In some extreme lensing cases, this time delay can be months or even years, meaning that astronomers can observe the same object at different points in its evolution simultaneously. This has practical applications beyond just being theoretically interesting. If the background object is something variable, like a quasar or a supernova, astronomers can observe it brightening in one lensed image and then predict when that same brightening will appear in the other images based on the calculated time delay. This provides a powerful test of our models of gravitational lensing and our understanding of cosmic distances. It also allows scientists to measure the Hubble constant, the rate at which the universe is expanding, using a completely independent method from traditional approaches. This is crucial because different measurement techniques have been giving slightly different values for the Hubble constant, a discrepancy called the Hubble tension that might indicate new physics or might simply reflect systematic errors in our measurements. Webb's lensing observations are also revealing the structure of dark matter halos around galaxies and clusters. Dark matter doesn't emit or absorb light, but it does bend light through its gravitational influence. By carefully modeling how light is lensed, scientists can map out where the dark matter is, how it's distributed, and how much of it there is. These observations are confirming that dark matter exists on all scales, from individual galaxies to massive clusters, and that it's absolutely essential for explaining the large-scale structure of the universe. Without dark matter's gravitational pull, galaxies wouldn't rotate the way they do, galaxy clusters would fly apart, and the cosmic web of structure we observe wouldn't exist. Some fringe theories have proposed that dark matter doesn't actually exist, that what we're observing is instead evidence that our theory of gravity needs modification on cosmic scales. These modified Newtonian dynamics theories, often abbreviated MOND, try to explain galactic rotation curves and other observations without invoking invisible matter. But Webb's lensing observations, along with many other independent lines of evidence, strongly support the existence of dark matter. The lensing can't be explained by modifying gravity alone. There has to be additional mass present, mass that doesn't emit light. The evidence is overwhelming, though scientists continue to search for direct detection of dark matter particles in laboratory experiments, hoping to identify what this mysterious substance actually is. Think about this carefully. 85% of the matter in the universe is something we've never directly detected, something we know exists only through its gravitational effects. We live in a universe where everything we can see, all the stars and planets and galaxies, all the light and heat and matter we can measure directly, represents only 15% of what's actually out there. The rest is invisible, detectable only through its influence on the visible. How does that reshape your understanding of reality? How confident can we be in our knowledge of the universe when the vast majority of its contents remain mysterious? The 10th and perhaps most profound discovery doesn't involve a single observation, but rather an emerging pattern across many of Webb's findings. The telescope is revealing that the universe's evolution has been faster, more efficient, and more complex than our models predicted. We've mentioned the surprisingly mature early galaxies and the unexpectedly massive early black holes. But this pattern extends further. Webb has found evidence of heavy element enrichment occurring earlier than expected, suggesting that the first generations of stars lived and died quickly, rapidly polluting their environments with metals. The telescope has observed complex organic molecules in a wider variety of environments than anticipated, suggesting that the chemistry of life is more universal than we thought. There's also emerging evidence, still preliminary and requiring confirmation, that some of the most distant galaxies Webb has observed might be even more distant than initial estimates suggested. If confirmed, this would push back our view of galaxy formation even further, to within 150 to 200 million years after the Big Bang. At these extreme early times, the universe was hotter, denser, and more uniform than it was just a few 100 million years later. The fact that galaxies could form under these conditions challenges our understanding of how structure emerges from the smooth, nearly uniform state of the early universe. All of this points toward a common theme. The universe is more precocious than we thought. Things happen faster, earlier, more efficiently. This might seem like a minor technical point, an adjustment to our timelines and models that matters only to specialists. But it has deeper implications. If galaxies, stars, black holes, heavy elements, and complex chemistry all emerged quickly in the early universe, then the conditions necessary for planets and potentially life arose earlier than we thought. This doesn't mean life definitely exists elsewhere, but it expands the temporal window during which life could have arisen, potentially allowing for civilizations far older and more advanced than humanity. Some scientists have speculated, and this is definitely speculation venturing into the realm of thought experiments rather than established science, that if complex chemistry and suitable planetary environments existed in the universe's first few billion years, there could be civilizations out there that have had a 10 or 11 billion year head start on humanity. Imagine what a civilization could achieve with that much time. Humans have gone from agricultural societies to spacefaring technological civilization in roughly 10,000 years. What could we accomplish with a billion years? Could we spread across the galaxy, engineer stars and planets, manipulate the fundamental forces of nature? The thought is simultaneously exciting and humbling. But let's step back from speculation and focus on what Webb's discoveries definitively tell us. They tell us that the universe is stranger and more wonderful than we imagined. They tell us that our models, while powerful and predictive, are incomplete, requiring adjustment and refinement in light of new observations. They tell us that every answer generates new questions. Every mystery solved reveals deeper mysteries beneath. This is the nature of science at its best. Not a static catalog of facts, but a dynamic, self-correcting process of discovery that continually reshapes our understanding of reality. Webb's observations have also highlighted the importance of international collaboration in modern science. The telescope itself is a partnership between NASA, the European Space Agency, and the Canadian Space Agency, with contributions from thousands of scientists, engineers, and technicians from around the world. The data it produces is made available to researchers globally, with observation time allocated through a competitive proposal process that evaluates scientific merit rather than national origin. Some of the most important discoveries have come from relatively small research teams, graduate students and early career scientists analyzing publicly available data and finding patterns that others missed. This democratization of access to premier scientific facilities is crucial for ensuring that good ideas, regardless of where they come from, have the opportunity to contribute to our collective knowledge. The telescope's journey to operation was itself a testament to human persistence and ingenuity. Webb's development took nearly 30 years, weathering budget overruns, technical challenges, and moments when the entire project seemed in jeopardy. The telescope's complexity is almost unimaginable. Its primary mirror consists of 18 hexagonal segments, each precisely shaped and positioned to function as a single 6.5-meter mirror. These segments are made of beryllium, coated with gold to optimize infrared reflection, and each can be individually adjusted by tiny motors to maintain perfect alignment. The telescope's sun shield, about the size of a tennis court when deployed, consists of 5 layers of specially engineered material that reduces the temperature from the sun-facing side, which can reach 85 degrees Celsius, to the cold side, which operates at -233 degrees Celsius. This temperature difference is essential because Webb's infrared instruments must be kept extremely cold to detect the faint heat signatures of distant objects without being overwhelmed by their own thermal emission. The telescope orbits not around Earth but around a point in space called the second Lagrange point, or L2, located approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the gravitational pull of the Earth and Sun balance in such a way that Webb can maintain a stable orbit with minimal fuel expenditure. The location also keeps the Sun, Earth, and Moon all in the same direction, allowing the sun shield to protect the telescope's cold side from all 3 heat sources simultaneously. But reaching L2 required a month-long journey after launch, during which the telescope had to execute one of the most complex deployment sequences ever attempted in space. Hundreds of mechanisms had to work perfectly, in sequence, in the vacuum and temperature extremes of space, with no possibility of repair if something went wrong. The fact that it all worked, that every motor fired, every latch released, every panel unfolded exactly as designed, is itself a remarkable achievement. Think about the people behind this achievement. Engineers who spent years designing a single mechanism, testing it thousands of times to ensure it would work when needed. Scientists who devoted their careers to planning observations they wouldn't execute until retirement or beyond. Administrators who fought to keep the project funded through political and budgetary challenges. Technicians who assembled components in clean rooms, working with precision measured in nanometers. The telescope represents not just technological achievement but the accumulated effort of a generation of dedicated professionals. People who believed that understanding the universe was worth the time, money, and effort required. And now, as Webb continues its mission, sending back transformative data week after week, month after month, we're confronted with the fruits of that labor. Every image, every spectrum, every data point represents both an answer and a question, both a confirmation of what we thought we knew and a challenge to assumptions we didn't know we'd made. The telescope is expected to operate for at least 10 years, possibly 20 or more if its consumables hold out, meaning we're still in the early days of its scientific mission. The discoveries we've discussed, as remarkable as they are, might represent just the beginning, the first chapter in a story that will unfold over the coming decade. What else might Webb reveal? Scientists have proposed observations targeting everything from the very first stars, those metal-free population 3 giants we've never directly seen, to detailed characterization of potentially habitable exoplanets, searching for the biosignatures that might indicate life. The telescope will study the formation of planetary systems around young stars, watching as disks of gas and dust coalesce into planets, potentially catching the planet formation process in action. It will observe the most distant and luminous quasars, probing the environments around supermassive black holes when the universe was young. It will map the distribution of dark matter by observing gravitational lensing on unprecedented scales. It will study the chemistry of comets and asteroids in our own solar system, the small bodies that preserve pristine material from the solar system's formation 4.6 billion years ago. Each of these observations has the potential to reshape our understanding, to provide that crucial piece of evidence that confirms or refutes a theory, to open up entirely new questions we haven't yet thought to ask. This is the power of new observational capabilities. You can't predict what you're going to find, because if you could predict it, you wouldn't need to look. The most important discoveries are often the ones that surprise you, the observations that don't fit existing models, that require you to think differently about what you thought you understood. Consider the broader context of Webb's mission in the history of astronomy. For most of human history, we studied the universe with our naked eyes, observing the motions of planets, the phases of the moon, the annual cycle of constellations. 400 years ago, Galileo turned the first astronomical telescope toward the heavens and discovered moons orbiting Jupiter, phases of Venus, countless stars invisible to the naked eye. Each new generation of telescopes has expanded our view, revealing new phenomena and new mysteries. The development of spectroscopy in the 19th century allowed us to determine the chemical composition of stars, proving that the same elements that exist on Earth exist throughout the universe. The invention of radio astronomy in the 20th century revealed an invisible universe of pulsars, quasars, and cosmic microwave background radiation. Space-based observatories like Hubble freed us from the blurring effects of Earth's atmosphere, providing unprecedented clarity. Webb represents the latest step in this progression, but it's important to understand that it won't be the last. Even as Webb conducts its observations, astronomers are planning the next generation of observatories. Ground-based extremely large telescopes with mirrors 30 to 40 meters in diameter are under construction. Future space missions are being designed to search specifically for biosignatures on rocky exoplanets or to observe in wavelengths that Webb can't access. Each new facility will have its own unique capabilities, its own scientific niche, and together they'll build an increasingly complete picture of the cosmos. But even as we look forward to future discoveries, it's worth pausing to appreciate what we've already learned and what it means for our place in the universe. We live in a cosmos 13.8 billion years old, containing hundreds of billions of galaxies, each with hundreds of billions of stars. We inhabit a planet orbiting an unremarkable star in the outer regions of a spiral galaxy called the Milky Way. The matter that makes up our bodies was forged in ancient stars and scattered through space when those stars died. The universe is governed by physical laws that we're still working to fully understand, laws that permit the existence of black holes and gravitational waves, quantum mechanics and relativity, structure and complexity on scales from subatomic particles to cosmic filaments spanning billions of light years. And somehow, through processes we're still trying to comprehend, the universe gave rise to life, at least here on Earth and possibly elsewhere. That life evolved, diversified, and eventually produced beings capable of wondering about their origins, capable of building instruments to study the cosmos, capable of recognizing that they are part of something vastly larger and older than themselves. You are the product of 13.8 billion years of cosmic evolution, the descendant of countless generations of organisms adapting and surviving, a collection of atoms arranged in such a way that you can contemplate your own existence and the nature of reality itself. The James Webb Space Telescope is one expression of that capability, one way that the universe studies itself. When Webb observes a galaxy 13 billion light-years away, it's examining the universe's own past, looking back at how things were when the cosmos was young. When it analyzes the atmosphere of an exoplanet searching for signs of life, it's asking one of the most profound questions intelligence can formulate. When it probes the nature of dark matter and dark energy, those mysterious components that dominate the cosmic inventory, it's pushing at the boundaries of human knowledge, exploring territories where our maps are still being drawn. Every generation thinks it's living in a special time, that the discoveries being made in their era are uniquely significant. And in a sense, every generation is right. The accumulation of knowledge is continuous, with each generation building on the foundations laid by their predecessors. But there's something genuinely remarkable about the current moment in astronomy and cosmology. We're living in the first generation that can observe the universe across almost its entire history, from the cosmic microwave background radiation created 380,000 years after the Big Bang to the ongoing formation of stars and planets today. We're the first generation that can detect and characterize planets around other stars, moving the question of life in the universe from philosophy to empirical science. We're the first generation that knows the universe is expanding and accelerating, driven by mysterious dark energy that makes up 70% of the cosmic energy budget. These are not minor technical details. They're fundamental truths about the nature of reality, and we've learned them within living memory. Someone born in 1920 would have grown up in a time when many astronomers believed the Milky Way was the entire universe, when the Big Bang Theory hadn't been formulated, when the existence of black holes was pure speculation, when exoplanets were science fiction. That person, if they lived to see Webb's first images in 2022, would have witnessed a complete revolution in our understanding of the cosmos, a transformation in our conception of our place in existence itself. And the revolution continues. Webb's discoveries are not endpoints but waypoints in an ongoing journey. The mature early galaxies will require new models of structure formation, sparking theoretical work that might take years or decades to fully develop. The characterization of exoplanet atmospheres will improve with each new observation, building toward the day when we might detect genuine evidence of extraterrestrial life. The observations of star-forming regions and complex organic chemistry will deepen our understanding of how planetary systems and potentially life emerge from cosmic chemistry. The studies of our own solar system will guide future exploration missions, helping us target the most promising locations in our search for present or past life elsewhere in our cosmic neighborhood. What drives this enterprise? Curiosity, certainly. The desire to understand is fundamental to human nature, as basic as the desire for food or companionship. But there's something deeper too, something almost spiritual, though you don't need to be religious to feel it. There's a sense that by understanding the universe, we're participating in something meaningful, something that transcends our individual lives and concerns. The universe is not required to be comprehensible to us. The laws of physics could have been opaque to human intelligence, too complex or too alien for minds that evolved to track game animals and gather plants on the African savanna. But they're not. The universe follows rules that we can discover through observation and reason. Mathematics, a language we invented to count and measure, turns out to describe the fundamental workings of reality with uncanny precision. Why? We don't know. It's one of the great mysteries. What physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. But whatever the reason, that comprehensibility makes the scientific endeavor possible, and telescopes like Webb are among our finest tools for pursuing it. When you see a Webb image of a distant galaxy or a glowing nebula, you're not just seeing something beautiful, though the images are undeniably beautiful. You're seeing evidence, data points that constrain theories and test hypotheses. You're seeing the universe as it actually is, not as we might wish it to be or imagine it to be. And sometimes, often actually, reality is stranger and more wonderful than fiction, full of phenomena that would seem absurd if they weren't actually real. Black holes where space-time curves so severely that nothing, not even light, can escape. Neutron stars where matter is compressed so densely that a teaspoon would weigh billions of tons. Quantum mechanics where particles can be in multiple states simultaneously until observed. Dark energy that's causing the universe's expansion to accelerate, potentially leading to a future where galaxies outside our local group recede beyond the cosmic horizon, forever invisible to future observers trillions of years hence. These are the realities that Webb and other scientific instruments help us understand. They're not comfortable truths. They don't put humanity at the center of creation or assure us of cosmic significance. But they are, as far as we can tell with our best observations and theories, true. And there's a kind of nobility in facing reality as it is, in accepting our small place in a vast cosmos, in finding meaning not through cosmic importance but through the act of understanding itself. As we close this exploration of Webb's 10 transformative discoveries, let's return to the question we started with. What does it mean that the universe is stranger, more complex, and more wonderful than we imagined? It means that our work is far from done, that there are still mysteries to solve, still questions to answer, still frontiers to explore. It means that despite all we've learned, we're still at the beginning of understanding, still children playing on the shore of an ocean of knowledge, to paraphrase Newton. The galaxies that form too quickly challenge our models, forcing us to reconsider the processes that build structure from cosmic chaos. The black holes that grew too massive too fast hint at physics we don't yet understand, processes operating in the extreme conditions of the early universe. The atmospheres of distant exoplanets we can now analyze bring us closer to answering the question of whether we're alone, a question that has haunted humanity since we first looked up at the stars and wondered. The complex organic chemistry scattered throughout star-forming regions suggests that the building blocks of life are universal, present wherever conditions permit. The detailed views of our own solar system's outer planets and moons reveal worlds of unexpected complexity, ice giants with hidden dynamics, moons with subsurface oceans where life might survive far from the sun's warmth. The deep field images revealing thousands of galaxies in a grain of sand patch of sky remind us of the universe's vast scale, the billions upon billions of worlds that exist beyond our immediate perception. The observations of gravitational lensing confirm Einstein's relativity while revealing the distribution of invisible dark matter that scaffolds the cosmic structure. The evidence for rapid chemical enrichment in the early universe shows us how quickly the cosmos built complexity from the simple hydrogen and helium of the Big Bang. And the overall pattern, the precocious universe that evolved faster and more efficiently than expected, suggests that conditions favorable for complexity, and perhaps life, arose earlier and more widely than we thought. These discoveries matter not just for what they tell us about the cosmos, but for what they reveal about ourselves, about our capacity for wonder, our drive to explore, our ability to work together across nations and cultures in pursuit of shared knowledge. The James Webb Space Telescope is humanity's gift to itself, a tool for seeing farther and clearer, for asking better questions and finding more surprising answers. And the journey continues. Right now, as you contemplate what you've learned, Webb is out there at L2, its golden mirrors collecting ancient photons, its instruments recording the secrets of the cosmos. Astronomers are analyzing data, making new discoveries, preparing papers that will reshape our textbooks and our understanding. Engineers are monitoring systems, ensuring the telescope continues to operate at peak performance. The next generation of scientists is being trained, preparing to take the helm when current researchers retire. And somewhere, a child is looking up at the night sky, feeling that same sense of wonder that has driven exploration for millennia, perhaps destined to become the scientist who makes the next great discovery, who answers questions we haven't yet learned to ask. What will Webb show us next? What mysteries will it solve, and what new mysteries will it reveal? Which of its discoveries will prove most transformative in the long run? Will it find definitive evidence of life beyond Earth, or will that prize remain just beyond reach, waiting for the next generation of instruments? Will it observe a supernova in a galaxy so distant that the explosion occurred when the universe was less than 1 billion years old, giving us our first clear view of how the earliest generations of massive stars died? Will it stumble upon something completely unexpected, some phenomenon we haven't predicted, some object that doesn't fit any existing category, forcing us to expand our conceptual frameworks to accommodate new realities? We can't know the answers yet. That's what makes exploration exciting. That sense of stepping into the unknown, of turning over stones to see what lies beneath. But we can be certain that Webb will continue to surprise us, to challenge us, to inspire us. The universe has never failed to exceed our expectations, and there's no reason to think it will start now. Each answer leads to new questions. Each mystery solved reveals deeper mysteries. This is the gift of science, the blessing and curse of being conscious beings in a universe we can study but perhaps never fully comprehend. So the next time you see an image from the James Webb Space Telescope, take a moment to really look at it, to think about what it represents. Those aren't just pretty pictures of space. They're data from the edge of the observable universe, photons that traveled for billions of years to reach a precisely engineered mirror, to be focused and analyzed and transformed into knowledge. They're proof that we can understand things far beyond our everyday experience, that human curiosity and ingenuity can reach across space and time to illuminate the darkness. They're reminders that we live in a universe of surpassing beauty and strangeness, a cosmos that rewards our attention with wonder and our questions with answers that only lead to deeper questions. And perhaps most importantly, they're invitations. Invitations to be curious, to ask questions, to seek understanding. Invitations to feel connected to something larger than ourselves, to recognize that we're part of the cosmic story, made of stardust and given the extraordinary gift of consciousness, the ability to know that we know, to wonder that we wonder. The James Webb Space Telescope is looking outward at the universe, but in doing so, it's also holding up a mirror to humanity, showing us what we're capable of when we work together, when we persist despite challenges, when we dare to ask the biggest questions we can formulate. The 10 discoveries we've explored are just the beginning, the first chapters in a book that's still being written. There will be more surprises, more revelations, More moments when scientists look at their data and realize they're seeing something nobody has ever seen before, something that changes how we think about the universe and our place within it. And in those moments, humanity takes another step forward, our circle of knowledge expanding into the darkness, light pushing back ignorance just a little bit further. This is the promise and the gift of the James Webb Space Telescope. Not just knowledge for knowledge's sake, though there's nobility in that, but knowledge that transforms how we see ourselves and our world. Knowledge that inspires the next generation to reach higher, to ask bolder questions, to build better tools and pursue deeper understanding. Knowledge that reminds us, in an age that sometimes seems dominated by division and short-term thinking, that we're capable of extraordinary things when we commit to long-term goals and work together toward common purposes. The universe is vast, ancient, and strange beyond imagining. But it's also knowable, at least in part, accessible to our questions and our instruments. And every time we reach out to touch it with our telescopes and our theories, it reaches back with gifts of wonder and understanding, with images that take our breath away and data that reshape our textbooks. The conversation between humanity and the cosmos continues, and instruments like Webb are how we listen, how we ask, how we learn. The 10 discoveries that changed everything are not endings but beginnings. Doorways opening onto vistas we're only starting to explore, questions that will occupy researchers for decades or centuries to come, mysteries that will inspire children who aren't born yet to become the scientists who finally solve them. This is the ongoing story of discovery, and we're privileged to be living in a chapter where the plot is thickening, where the stakes are rising, where the most exciting revelations might still lie ahead, waiting for us in the data that Webb continues to gather night after night, alone in the darkness at L2. Humanity's faithful eye on the infinite.